Okay, thanks for the introduction. I'm here at Fraunhofer IWES, based in Bremerhaven. Some of you maybe will visit the institute, or at least some parts of the institute this afternoon. For those who are not able to visit it, I have a short introduction slide. Fraunhofer Institute for Wind Energy System is dealing with applied research on the entire scale of wind energy and wind turbine technology. So we are dealing from nanoparticles in materials analysis, and also to the large scale aerodynamics in wind parks. Last year we had our 10 years anniversary, and so you can see on the slide on the big screen in the middle the milestones we had, and we have different locations. And in Bremerhaven, for example, we have the rotor testing facility, also the dynamic nacelle laboratory, and we have also a floating lidar buoy. And in Hannover, for example, we have a testing facility for support structures. So this is close to the previous presentation. And just recently in Hamburg, last year, we have a new testing facility for the large bearing test bench. But we are also dealing with floating technology, and we are in the part of the project AFFLOAT, which is short for Accelerating Market Uptake of Floating Offshore Wind Technology. And that's what I want to present today. It's an Interreg Northwest Europe project, and its duration is planned for 4 years. It started end of 2018, so it's expected to end in 2022. It's funded by ERDF with 14 million euros, and the overall budget of the project is around 31 million euros. And the main motivation of this project is to develop a high survivability, cost-competitive floating technology, and to also show this maturity of the technology by building a demonstrator on the west coast of Ireland. So we are in total 8 project partners coming from the Northwest Europe region, and dealing with the different aspects for developing such a floating wind turbine system. And we are also collaborating with some associated partners, which are mainly supporting in long-term studies, which I will also present at the end of my presentation. So we have 3 main tasks and goals in this project. The first is, of course, to set up the test site and get it connected to the grid, where later the floating wind turbine system will be installed. So what is the test site? We have chosen AMITS. It's the Atlantic Marine Energy Test Site, which is developed by the project partner SEAI. And as you can see here on the picture, there's really harsh weather conditions. And in detail, we have at the test site 2 different sites available, which we can use. Test site B is closer to the shoreline, and test site A is a bit further away. But test site A also has already twice as large water depth. So we are here already at 100-meter water depth. And here on the card in the middle, you can see it's on the west coast of Ireland. And why did we choose AMITS? As you have seen in the previous slide, already close to the shore we have deep water conditions where we can test a floating technology. Furthermore, the seabed is sandy, and this is good for the cable and moorings. And what's the main important point was that at AMITS we have wind and wave conditions of world class. So the environmental conditions are really extreme. We deal with significant wave heights of around 16.7 meter. For example, in 2013, there was a 12-meter wave height measured. And also the wind speed is very high. So the values presented here, average wind speed of 8.8 and maximum wind speed of 35.1 meter per second are given for 1 meter above sea level. So if you scale it up for hub height, it's really large wind speeds what you have at this location. And so we have chosen this site because if the system survives there and we can show that the system is working at this site, we can install it at any place everywhere in the world. For the site development and for establishing the test site and the grid connection, right now there's ongoing work, especially in environmental impact assessments, also doing leasing awards, planning the substation permission, so getting everything permitted. But further work is also on further site investigation on geotechnics. Then in the end performing the environmental surveys, and the main goal in the end is to deploy the cable out at the site and build the onshore substation and the grid connection. So the second main task of the project is of course the development of the floating technology and the installation of the technology offshore west of Ireland. So what system are we dealing with? Our project partners is Saipem, who has developed a floating wind turbine system. And this is a pendulum lightweight structure which shows a very low motion response even in extreme sea conditions. So what you can see here, it's a semi-submersible floater which consists of tubular elements. At the bottom it's a counterweight which is connected with tendons to the steel structure. And we only need simple mooring lines because of the low motion of the floating system. And we also have a lazy wave dynamic cable. So to come to the concept first, I think most of you maybe know the three main stabilizing mechanisms of floating systems. These are either ballast stabilized, like this high bend spar buoy, or you have a tension leg platform which is stabilized with a mooring system. I think the next presentation by Frank Adam is dealing on this system. And the third stabilizing mechanism is semi-submersible or barge type, so based on the buoyancy. And our system, which we are using in Afloat, it's a mixture of everything. The buoyancy is given by the steel structure. Then we have the counterweight, which is at a deep position. So this is like representing the spar type. And we also have tendons which connect the counterweight to the steel structure. Just to give you some information on the dimensions, what you can expect if you place, for example, a 10 megawatt wind turbine on the floater, how deep the system will go below the still water line, and which weights the system will have. Below the steel structure we have the counterweight, which is a circular steel bucket which is filled with a heavy ballast material. This is mainly a high density material. For example, we can use Magna Dense. And this steel bucket is connected with tendons to the tubular steel elements, this hexagon at the top. For the mooring system, as I already said, we need just a simple mooring system because the entire floating system shows a very little response, even in extreme environmental conditions. But still, we decided to go for 6 mooring lines. 3 mooring lines are also possible. And we also need small chain diameters and also have a reduced maximum braking tension length. So also the entire radius of the footprint of the moorings is comparable short compared to other floating systems. In our case, it would be around 550 meters. One aspect on the fabrication of this floating system that's also a benefit of this design, because it can be fabricated in series. You start, everything can be assembled onshore. And you start with a vertical central column, then you connect the horizontal braces and the vertical braces. In the end, you connect also the braces for the stabilization to the central column, and you also include the ballasting system, which is included in the tubular elements. And afterwards, the mating of the turbine happens also on harbor side because of the shallow draft of the entire floating system. And for the installation, we can use common vessels, which are already known and used for offshore installation techniques, because we can tow the fully assembled floating system offshore. And we don't need any heavy lift vessels because the turbine is already mated in the harbor side. And first we need to install the counterweight with the moon lines, and then the floater is placed on top of the counterweight and connected with the tendons to the counterweight. Just to show you to which level we have already developed this floating system, Saipem has already performed some water tank tests in a scaled model. And the test results showed a better performance than it was expected based on the numerical calculations before. So it showed very little motion response of the floating system, even in extreme environmental conditions. And now with the Afloat project, we will reach technology readiness level 7 by installing the demonstrator. And afterwards, a commercial project could be possible. And this is also something for the future when we are looking at the trend of for the wind turbines, which are increasing in size. Also, the floater needs to be adapted, and the floating system is fit for the larger wind turbines, because on the one hand you have an increased mass of the turbine and increased hub height, but the floating system itself, the steel structures do not change that significantly. You only need to have elongated tendons and a larger ballast in the counterweight at the bottom. So this floating wind solution is also fit for the next generation of turbines. And this leads me to the final goal of the project, which also deals with the future aspects of the technology, as we also develop a floating offshore wind development plan. So what are the main aims of this plan? There are three. So we want to educate the investors and project developers about the technology maturity. Then we also want to have a coordinated change in the perception of the private sector, so that they want to invest in the floating offshore wind technology. And the third aspect is to create a supportive policy environment and also an active supply chain. And in the Afloat project, we of course focus on the Northwest Europe region. So for this, we prepare in the end a floating offshore wind development plan. We aim to have an agreed vision for the future of the floating offshore wind development. And with this, we also want to aim to accelerate the market rollout of the floating offshore wind technology. How do we want to achieve these aims? We are working with on three working groups on the three main topics, so the maturity and investability, then the policy environment, and the third topic is the active supply chain. And in these working groups, our associated partners are also cooperating. And we also plan to have some showcase events and some site visits to real-life operational demonstrations, including ours as well in the end. So to conclude, in the Afloat project, we are now on the way towards technology readiness level 7. We are working with a cost-competitive lightweight structure design, which shows high survivability even in extreme environmental conditions. and which is also fit for larger turbines. So in the end, we can show that the floating offshore wind technology is already major, and we also aim to have an agreed vision on the future of floating offshore wind development. So with this, I want to thank you for your attention, and I think if there are any questions, maybe you already want to write down.
Yes, thank you very much, Mareike Leimeister. That's major thumbs up here. Are there any questions from the audience? There's actually two of them, so we wait for them. The meantime, it's always good to see what good things are coming out of IWES Fraunhofer here in Bremerhaven, so that research is worth the cost and the effort, so to say. So we're just waiting for the maybe one question for the meantime. Is there any maximum or minimum water depth to install this? Depending on the turbine size, I suppose, but
Yes, definitely. So it highly depends on the turbine size. Right now we are investigating 2 megawatt, between 2 megawatt and 6 megawatt. That's also relevant for the environmental impact assessments, because you also have different blade tip heights, but also for the water depth. So if we are going for a 6 megawatt wind turbine, we definitely need the 100 meter water depth of site A. We can no longer go for the 50 meter water depth of site B.
okay.
But with 2 megawatt, we would be possible also to go for 50 meter water depth.
Okay, thank you. So we have 3 questions. I'll just start with which one I can read best. Okay. Sorry for that. Okay, so I read out that one here. What is the draft of the floater? What is the minimum installation depth of water? You probably answered that already. And what is the O&M concept for heavy maintenance, such as blade exchange?
So I think the first question I had already answered. It's similar to your question. For the maintenance, it depends. So a minor maintenance work can be done offshore, but if there's some major maintenance required, you can also disconnect the floater from the site and tow it back to the harbor site. If this is a cheaper and maybe with respect to the time, a better solution in the end.
Okay, thank you. More questions coming in, so this you probably hit a spot here. So I cannot really read that one. Sorry, I'll have to take that later because I cannot really read it. Here's congrats to the results. What about the substations? Are they floating too, or are they distant from the array?
So for this, we have AMETS is already a developed test site, and there's a cable connection to the shore. At the moment, it's one single prototype demonstrator, but I think for a wind park later, we can also think about a floating substation, but that's at the moment not yet discussed.
Okay, but yeah. Well, let's see where this is taking us. So here's a question from Wei Chen from Mingyang. Which turbine is planned for the full-scale demonstrator?
As I said, we are investigating a size between 2 megawatt and 6 megawatt. At the moment, I cannot say any specific wind turbine type or name. But I think if it's decided and if it's transported to the site, you will get the name out of the news, definitely.
Okay, there's somebody indicating it's a stupid question, but there are none. If the turbine is swimming or floating, why isn't it sinking? So what is the Auftriebskörper?
Okay, so as I let me see if I can go shortly to the slide. I had shown you the 3 different stabilizing mechanisms, and in our concept, the buoyancy components are the tubular steel elements here on the side. So they are mostly hollow. We also have a ballasting system, but they don't. This ballasting system doesn't cover the entire tubular elements. So with having hollow elements, you have the buoyancy, which make your floating system floating and not sinking anymore. And also the displaced water by the counterweight, it's also some buoyancy. But in the end, that's everything calculated, and we definitely ensure that it's not sinking.
That would be good, I guess. Okay, so now thank you for writing that question again. What are the similarities or differences compared to the tetraspar? It's a question by Heinrich Stuster. And can the counterweight be pulled up? Afterwards, a completely different question there. But
okay, so basically from the principle, it's similar to the tetraspar from steel. Of course, the counterweight is different. The steel concept also considers a spar, a semi-submersible, or a TLB type and design. In our case, it's a circular steel cylinder, and for the tetraspar is a triangle. But I think from the design and from the stabilizing mechanisms, it's very comparable to this concept. And with respect to the counterweight, yes, definitely you can change the position of the counterweight. I think at the moment it's not controlled, so you cannot change it during the operation, but this also allows you some adjustments for different site conditions or a different wind turbine, so that you can maybe use the same steel structure, but by shifting your counterweight with increasing the tendons or shortening the tendons, you can maybe allow for a different operational stability in different environment conditions depending on your site.
okay, thank you. I have yet another question, and if you agree, we would just extend the time here because the interest seemed to be very large. What are the benefits of this design over others? So, what's your market analysis, basically?
So basically, it's the main goal or the main problem at the moment with floating wind technology is that they are not yet cost competitive, and the market rollout has to speed up. And for this, this design is on the one hand lightweight, so this makes it already cheap from the material used. It can be fabricated in series. This also makes it cheaper when we are going for large series fabrication for wind parks. And it's also adjustable and usable for different sites. Of course, we cannot go in very shallow water, but we are already in the intermediate water depths. As I said, site B was 50 meters, and that's a site where you can maybe also use jackets. So you can use this floating system for intermediate water depths, but also for very deep water depths. And as also shown in the presentation, the design doesn't change that significantly, even if you scale it up for larger wind turbines. But what is the current trend in the wind turbine technology? So I think there are many significant benefits of this design.
Okay, so thank you very much. I think, yeah, I hope we covered all the questions. Sorry for going a bit past the time, no problem. There seems to be a lot of interest, and your contacts are in the presentation, of course, and everybody's welcome to get in contact with you. And yeah, let's see where this thing is going. Good luck. Okay.
Thanks for the interest.
All right.